Welcome back to the lab. Today we're going to mix things up just a little bit. We're going to be talking about the UPS we just designed and finished testing. We designed this collection of circuits with the intention of converting 700 watts of low voltage DC goodness to 120 volts AC. This process requires some serious power converter design, and ours was, unfortunately, not quite up to par. Wait a minute. This isn't mixing things up at all. We love power conversion. We talk about it all the time. Well, I guess I've already done the intro. May as well dive in. Before we get into the details, let's just scratch the surface. Many moons ago, we talked about some requirements for this project. Those turned into this table. This table of 17 things that we want to accomplish. Let's sort these goals based on whether or not we accomplished them. Looking at this list, there's actually quite a lot that this UPS is capable of. Our UPS output is capable of being either ground or neutral referenced. This is important for safety reasons. Our UPS is designed such that in any single fault condition, an upstream 20 amp 120 volt circuit breaker will not trip. This is guaranteed by the input power fuses, but is also enforced in software through our overload hiccup routine. Our UPS implements input transient voltage protection on the mains input as well. This one kind of feels like cheating because it's implemented in the input filter of our off-the-shelf AC/DC power supply, but it's there. When laying out the PCB, we followed guidelines captured in IEC 60601 to implement creepage and clearance. This, objectively, provides us with a high level of confidence that the design will pass high-pot testing, even if we haven't performed the test yet. Our UPS is designed to operate in a steel chassis such that no flames can escape the enclosure if push comes to shove. The fans and heatsinks present in our UPS are definitely capable of keeping the system cool, too. Now, there aren't any daughter curds in our system right now, but these are able to be mechanically stabilized by screws if necessary. We have a NEMA 520R connector available for supplying power from the UPS to downstream loads. This connects to our screw terminals. Note, we should probably optimize this a bit more. Right now we're using a cut mains cord, not exactly what I'd call ideal. The battery backup source is capable of supplying full power to the UPS. Our UPS is capable of switching from primary to secondary DC input, and we can supply the inverter with whatever DC input seems most appropriate at the time. That's a long list of things done, but there's still more to talk about. There are many features that we see strong potential for working, but just didn't see the value in pursuing further until the core functionality was up and running. For example, we haven't run a high-pot test on the board yet, but once we've done our testing, you better bet that a 3.5 kV high-pot test is going to happen. We didn't finish implementing the USB HID power device class yet, but we saw our microcontroller behave as a native driverless USB device. The microcontroller has all the information it needs to build up that report, since it can request whatever it does not know from the inverter microcontroller. Our UPS has no knowledge of input frequency, so right now it doesn't change over to backup power if the input frequency is out of range. It's a pretty small thing. It's an especially small thing because the architecture that we're using doesn't directly depend on input frequency. If input frequency is wrong enough to matter, that'll cause our DC power supply to fail. This in turn will trigger a transition over to battery power. So we do it through proxy. I'll say we do it through proxy. Okay, what about things that absolutely definitely don't work as well as we need them to? Well, the power output of our UPS cannot exceed 120 watts. We're stuck at around 90, and 90's really pushing the limit of our current design. There's no common or differential mode filtering on the AC input of the UPS, well, except for what's implemented in the off-the-shelf power supply. Our UPS does not cross over from primary to secondary DC input in 0 milliseconds, taking a sluggish 1.3 seconds to make that transition. Finally, the battery charger is incapable of charging the batteries at a reasonable current level. 0.2 amps just isn't going to cut it. I mean, technically, we might charge the batteries eventually, but it's slow enough that I can safely call this a fail. All things considered, that review of how well our UPS is performing, I've seen worse. We crossed a lot of critical features off the list, and that's awesome. What's more, the features that we just listed can be boiled down, in my opinion, to optimizations. There's a lot of room for improvement here, but when push comes to shove, the feature set of our UPS is very, very close to where we'd like it to be. Speaking of where we'd like to be, the beach. There's a couple subsystems in particular that we need to improve. The first one isn't really a subsystem right now, but I didn't do a great job of architecting the low voltage DC power supplies in the UPS. For better or worse, I got distracted by all the big fun power converters, and I didn't really want to spend too much time making the simple box. Now, that's a bit of a miss on my part, and we'll have to do better next time. Specifically, here's what we need. A low current 15 volt DC power supply for driving the FETs in our 700 watt DC to DC step-up converter, a 5 volt supply capable of supplying at least 2 amps for the microcontrollers, a 5 volt analog reference voltage, an 11 volt power supply for driving the fans, a 27.3 volt power supply capable of supplying at least 4 amps for charging our lead acid batteries. That's a lot of supplies, and we're missing one of them on our board right now. That small army of switch mode power supply modules is starting to feel a bit lazy in retrospect. It's not very efficient with our board space. What's worse, being lazy actually ended up making more work for us in the long run because we need to hand solder all the modules into the board. The tolerances on these voltage rails isn't really anything special, so they can be built down to a price. I could, and perhaps should, have done that. After all, I probably spent more time installing and tuning the output voltage for the 7 modules than they were worth. If I could refine this part of the architecture, I'd make one pre-regulator to accommodate the massive input voltage range of the system. With that done, we can synchronize the rest of the power supplies and generate whatever voltages are required. I'll have to keep that in mind going forward. Another big area for improvement is the push-pull converter. At first glance, I didn't appreciate just how the 3 following points could combine to create a really big problem. I didn't realize how difficult it can be to optimize the transformer for isolation and minimize leakage inductance at the same time, because I was never winding it myself. How sensitive the push-pull architecture is to leakage inductance, because, well, this is our first time using this specific architecture and getting bitten by these bugs, and how that high turns ratio can make the push-pull converter even more sensitive to leakage inductance. These are a few pretty subtle things that combined is we ended up with a push-pull converter which is sensitive to leakage inductance, with a transformer we wound ourselves and didn't optimize for leakage inductance, and a high turns ratio that made the reflections a higher magnitude. Wow. So our solution, well, where we're at right now is 200 volt ringing with a 12 volt input, meant to go up to 40, which, I mean, if this thing scales linearly, that's a lot of volts. Perhaps I don't have the solution, but a solution might be simply to consider a different topology. The full H converter is pretty similar to the push-pull in theory, which allows for some reuse in our transformer design. The full H converter helps, in part, to eliminate the issues that we saw with the hundreds of volts being generated by the leakage inductance of our transformer, and it does this by providing either active or passive clamping to both a voltage rail and to ground. This may effectively eliminate the need for the massive snubber, though we'll probably still need something. We'll have to spend some time thinking about this architecture and see if it'll work for our application. This, of course, all hinges on whether or not we can get leakage inductance under control. If the leakage inductance can't be managed appropriately, voltage regulation will fail. That said, we shouldn't hit any roadblocks while increasing the input voltage for the full H converter. Therefore, leakage inductance being too large will likely boil down to not meeting the minimum input voltage requirement and FETs not exploding. DC input crossover time is another huge opportunity for improvement. Put simply, the crossover time was just too slow. Unfortunately, the faster we switch from one input to the other, the more likely we will be to blow something up or damage the relays. There's naturally a compromise between power transfer time and timing margin, and we just need to do something about that. I have a couple ideas, but they aren't well formed, so I'll reflect on the faults and failures of this UPS for a few days and start to formulate a plan for phase 2. That's where our head is at around the phase 1 UPS. I think that as a first prototype, it came together really well. We implemented nearly all of the features required, and we found enough glitches that, 1, we aren't really satisfied with its performance, and 2, now we're getting hungry to do better. It doesn't feel right to up and walk away from this design challenge when it's only half finished. I know this project has been taking a while, but just for a moment, let's entertain the idea of a second prototype UPS. We'll start walking through the design steps, focusing on leveraging simulation and analysis to gain a high degree of confidence that this UPS will function. Now that we've had a chance to prove out many of the required features at a high level, but a low power level, but we've kind of walked through the steps once and we've gotten bitten by a lot of bugs. 10 out of 16 requirements isn't bad, but it's not great. If you want to see 700 watts, then subscribe to be notified of our future videos where we'll kick off phase 2 of this project and dig into some PFC design. I think that this UPS is good, but it's on a path to becoming amazing. If you think so too, let me know by hitting the like button on this video, chatting with us on Twitter, or leaving a comment letting us know what's on your mind. Most of all, I hope that you learned something great today, and I hope to see you again soon. So thanks for watching EE for Everyone, and thank you for staying till the end. Bye!